Good afternoon, everybody. Thank you for being here. This is one more session of our beloved Quantum Research Center seminar. And today I'm very, very glad to have here with us Professor Roger Melko. This is very special for me. I think that Roger was the guy that taught me what machine learning was in a course that they gave in Sao Paulo a few years ago. That was very nice. So it's really a special meaning for me to have him here. Professor Melko is a theoretical physicist. He works on computational strategies for condensed matter, quantum information, and other many-body systems. He's a professor at the University of Waterloo, Canada, and associate faculty at the Perimeter Institute for Theoretical Physics, also in Waterloo. He's written many papers. He's had several awards, already supervised lots of good scientists that have already become mature scientists themselves. And he's involved into so many things with startup incubators that is really amazing how he manages to do that. And so it's really a pleasure to have you here, Roger. Thank you very much for accepting the invitation to give a talk to us. Hopefully we'll have the chance to host you physically over the next couple of years in Abu Dhabi sometime. And please go ahead, proceed. Thank you.
Absolutely. Okay, thank you so much, Leandro. Let me start by sharing my screen just to make sure it works. Okay, great. It's a pleasure to be here. It's fun to see out there, in the audience. That's pretty cool setup you guys have. I've had a great, since I got the invitation to give this talk, I've had a great time looking at your website and learning about the Quantum Research Center and all the amazing stuff you guys are doing. So we have a lot of connections. I can't tell the video's small, but if Stavros, if you're out there, hey, how you doing? Oh, I see a hand. Hey, good to see you again. So here I am in your old home, the Perimeter Institute for Theoretical Physics. And what I'll be doing is talking a little bit about some of the research that we take here on the kind of the intersection of machine learning and quantum simulation. And I'll explain what I mean by that. Hold on, I'm just going to try to find my mouse here. Well, I'm just going to stop share and try this again. Sometimes with Keynote, I don't know why, but I lose my mouse. Okay, we'll go on without it. Okay, so here's my group. This is a snapshot of kind of the current state of my group since the end of the pandemic, sort of, outside of my house. And on the right-hand side, you'll see two important contributors to the work that I'm going to talk about. One's Juan Carrasquilla, who's a faculty at the Vector Institute for Theoretical Physics here nearby in Toronto, Canada. And at the top right, you'll see Giacomo Torlai, who was a student of mine who did a lot of the work on restricted Boltzmann machines that I'll show in this talk, and is now a research scientist at AWS, that's Amazon, their quantum computing division in Pasadena that's associated with Caltech. So you'll see how maybe some of the ideas I'm talking about here relate to quantum computing and so on. So I really want to talk about quantum simulation and simulators and what the difference between simulation and simulators is. And this ties into quantum computing through sort of Feynman's original, vision for what a quantum computer is that's related to this quote. If you want to make a simulation of nature, you better make it quantum mechanical. So as Leandro mentioned, I'm a condensed matter theorist. So I did my PhD in UCSB under Doug Scalapino, who is a famous cuprate, super high temperature superconductor theorist. And, the problem that I guess we were sort of interested in, in strongly correlated electrons at the time was the Hubbard model. And I've shown the Hamiltonian here. And the Hubbard model is, is kind of the quintessential, I guess I would call it, unsolved problem in condensed matter physics. You know what I mean? And it has to do with, the interactions of electrons in the two-dimensional copper-oxygen planes in something like YBCO or some of these other ceramics that, superconduct at liquid nitrogen temperatures. And the issue with, the reason I say it's kind of like an unsolved holy grail in some sense is that the mechanism of high temperature superconductivity has never been tied to the microscopic model that we know underlies the physics, okay? And so the model is really this Hamiltonian on a two-dimensional square lattice. And what we wish we could do is kind of understand the physics of that. And by that, I mean, calculate correlation functions, either in the ground state or in some excited states, calculate the properties of low-lying excitations, topological defects, dynamical properties, and so on. And when I was a grad student, I remember people told me, cold atom simulators are coming along. We're going to be able to physically implement, the Hubbard model and interacting electrons inside of these simulators. And by what I mean, I've illustrated on the right there, sort of the idea that the tunneling and interaction parameters of the Hamiltonian could be transferred, and implemented in a highly controlled programmable device. So these are, in the material, you have very little control over the interactions. But the idea is in sort of an analog quantum computer, this or other models could be implemented in a device where they could be tuned with a high degree of control. And so that's often what we call a quantum simulator. And quantum simulators can be, any substrate in principle that is programmable and has a lot of control. For example, we see a lot of work coming out of the superconducting quantum circuit community, trapped ion community. In the middle, I'm showing a Rydberg atom quantum simulator that I'll talk mostly about in this talk. Okay, so just to clarify, let me know if my slides aren't progressing. It looks like they are. Just to clarify, quantum simulation, I've said it in two different contexts now, and I really want to just sort of explain a little bit more what I mean when I say simulation. So I'm again a condensed matter theorist. I specialize in computational methods. And so most of my kind of training and my work has been on the left-hand side of this slide, which is Hamiltonian-driven, what I call Hamiltonian-driven simulation. And that's just kind of the, what I mentioned is that, I have a material. What I've illustrated there is lithium holmium fluoride, a single crystal of lithium holmium fluoride. And I think I understand through the chemistry and the crystal field interactions and everything, the model, or a simplified low energy model for that material. And that model is a Hamiltonian, and I've illustrated a transverse field Ising model there, which is the quantum Hamiltonian that describes lithium holmium fluoride. And I would typically imagine using that Hamiltonian to drive, to simulate or to understand the ground state properties and so on. And it could be equilibrium, they could be finite temperature, and they could also be dynamical properties that undergo some sort of unitary, if the wave function undergoes some unitary evolution or so on. So I'm calling that Hamiltonian driven. That's computational strategies to kind of understand, models. On the right-hand side is, quantum simulation from the quantum computing perspective. That's where I have projective measurements that come from a highly controlled quantum device. Okay, so I have a device, I prepare that Hamiltonian in the device, or those interactions in the device, and then I have access to data, something like projective qubit data that comes from that device, and then I could leverage that data to do something with. And that data that I've shown in that square is actually Rydberg occupation data, which I'll talk a lot about. So the data-driven strategy is the idea that I've kind of progressed from the crystal, that the original material or matter that I'm interested in to an abstract model, and then I've implemented that model on a highly controlled device. And now that device gives me all sorts of data. And again, it can be equilibrium or dynamical, because I can make a circuit, in a quantum device that not only, prepares a state, but it can also apply some unitary evolution or even non-unitary evolution to the state. So I'll try to clarify which side of simulation I'm talking about via Hamiltonian versus data-driven. And I only want to say very, quick, very short, kind of one slide on the Hamiltonian-driven setting. So even though this is my bread and butter, I've been working on this for decades, I really want to talk about the data-driven setting. So the Hamiltonian-driven setting is the idea, again, that we're solving numerically on a computer for, properties of a model. And we have very highly successful techniques that all of us in our field use for simulating many-body systems, particularly tensor networks, things like quantum Monte Carlo, and so on. And all of these methods has their own strengths and weaknesses. So for example, on the left, we're used to understanding the field of tensor network simulations, including the famous density matrix renormalization group, through the entanglement structure of the Hamiltonian, the entanglement structure of the wave function that we're interested in. And as long as the entanglement of a quantum state is sufficiently low, and I've illustrated an area law entanglement, then we expect that tensor network methods will generally work, especially in one dimension, okay? Higher dimensions, maybe we have some issues with. For quantum Monte Carlo, we're very used to talking about the sign problem. The Hubbard model is a famous example of the sign problem. And I'll talk quite a bit about the sign structure of Hamiltonians and how the sign structure affects the computational complexity. But generally, quantum Monte Carlo is very successful at simulating for equilibrium properties as long as the off-diagonal matrix elements of the Hamiltonian follow the structure illustrated. That is, they're all negative, and I'll talk more about that. And finally, methods like variational methods. So if you have variational Monte Carlo or something like that, we basically have a parameterization of a state, and we're jiggling these parameters, according to the variational principle. And basically what we have to overcome there is the optimization cost of this jiggling, or in some sense, the ergodicity cost of sampling these parameters. And that also relates to quantum Monte Carlo. So again, that was my lightning introduction to Hamiltonian-driven settings. And the point is that, not all Hamiltonians that we're interested in, like for example, the Hubbard model here, can be successfully attacked by these Hamiltonian-driven strategies. So now we want to ask the question, if I can prepare, these interactions in an experimental simulator, right? And I can get data in the data-driven setting, how does this compete with or complement the Hamiltonian-driven setting that I've illustrated here? So I'm going to turn to the data-driven setting. So the data-driven setting is really the idea that I have a quantum computer or an analog quantum device, a highly controlled, programmable device that I would call an analog computer, perhaps. And I'm really tasked in some sense with understanding what's in that machine and then leveraging, controlling it and leveraging it. And so, there's a feedback loop that already exists, which is well understood between, quantum computers and classical computers that has to do with readout and control, and maybe at a higher level design. And I'm just going to focus on sort of the readout aspect for most of this talk. And what I want to know is, like, if I can prepare a Hamiltonian or a model on the quantum device, how much information can I really get about, the correlations, the excitations, or whatever's happening inside that device, leveraging how do we know what's the content of a quantum state, leveraging measurements, like projective measurements of the qubit states, which are distributed according to a probability distribution, right? So that's the Born rule. So this is where the analogy with machine learning comes in. I have a quantum device, I'm producing data from it. My data vectors, I might have D data vectors that I've labeled X. So I have X1, X2, X3, all the way to XD, right? And each one of those vectors contains a array of qubit projective measurements. So either in the +1, -1, or plus minus h bar over 2, or 0 and 1, or 1 representation. Okay, so I have as many columns, if you will, in one of those vectors, or many elements in one of those vectors, as I have qubits in my device. And my goal for this talk will be to just take only those projective measurements and to learn a parameterized model of the state that underlies the data. So on the right-hand side, I see my laptop. I see some sort of neural network in there. I've labeled parameters with lambda. And what I want to do is find a way to represent and to reconstruct, whatever's in that quantum black box in my laptop only through those projective measurements. So that's a different setting than the Hamiltonian-driven setting, right? Where I have a Hamiltonian and I want to produce a model or something in the machine. Here I'm driving it with data. So the tool that we use to do that is called a generative model. And so I've used simulation in 2 contexts. I'm also using model in 2 contexts. part of the problem here is that generative model comes from the machine learning literature. And so I'll explain a little bit what a generative model is. So a model is something that we train from data. So we're using it to model the unknown probability distribution. And if I look here in my quantum device and I see this blue probability distribution, I'm just going to call that P of X. So what I want to do is basically reconstruct P of X or model P of X using the parameters of some sort of model, which I'll explain. And I'm calling all those parameters lambda. So how do I do that? How do I adjust parameters in a model? And I'll explain, and you can guess these parameters are going to be things like weights and biases of a neural network. The way I would do that is I have to define a cost function. And unlike the Hamiltonian driven setting where my cost might be the expectation value of the Hamiltonian, or like the variational setting, I don't really have the Hamiltonian here. Everything's driven by data, right? So I can't a priori assume that I might know the Hamiltonian, at least for the reconstruction. So we define a cost function related to the relative entropy between the unknown distribution in the black box and my parameterized model, which I'm in the process of explaining. And the standard cross entropy formulation is called the Kullback-Leibler divergence. And so you might have also heard of things like maximizing or minimizing a log likelihood or maximum likelihood methods. So these are essentially equivalent, and you can imagine how those two equations relate to each other. And what the Kullback-Leibler divergence does is define an optimization problem. And so really you've taken the task of modeling, your black box. I want to model my black box with a bunch of parameters, and you've turned it into an optimization problem by defining the Kullback-Leibler divergence. And then once you have that optimization problem, you have that cost function, you can imagine you take the gradient of that thing and you can update parameters via some sort of gradient descent. It's sort of as simple as that. And so why do we do this? I mean, the first question is, why would you ever worry about some sort of model? Why not just reconstruct the probability distribution from a frequency histogram, like on the left-hand side here? And the point is, in all modern quantum computing experiments, we're severely limited by the amount of data, that we have access to. And really that's the point. We're severely limited by the experimental shot budget. And, in the kind of modern example, it depends on of course, on the device. If you have a trapped ion quantum computer versus a Rydberg atom quantum computer, the frequency of measurements is very different in those two things, those two setups. But, this is all about, scalability and pushing things to the largest number of qubits as possible. And so at some point, you're really going to find yourself, relatively limited in shot budget. So generative models help, depends on your perspective, but they either help to interpolate or extrapolate the distribution, on a limited amount of data. And so on the right-hand side, I've imagined how this looks. So on the right-hand side, I have blue is data drawn from the same distribution. You can guess what it is. It's a Gaussian. I was lazy. I did it in Wolfram Alpha, I think. And so, if I have a small number of measurements, I get kind of a choppy histogram that has, gaps in its likelihood. And so if I wanted to have the likelihood of something like minus, I don't know what, 5.0, I might not have a data point there, right? But if I fit parameters, so if I use that data to fit the parameters of the red curve, and again, this is a Gaussian, so there's only two parameters, a mean and a standard deviation. You see exactly how you get, a very good fit to the left-hand distribution, which is taken over tens or hundreds of thousands of samples. So this is just kind of a very simple example of how a generative model works. Instead of reconstructing the entire frequency distribution, you fit a number of parameters that I'm calling lambda. And what neural networks give you, and other types of machine learning models, is they give you a way of systematically improving the representational capacity of your model by increasing things like the weights and biases. Okay. And so unlike if I was trying to fit a Gaussian where I only have two parameters, if I pick something that's a universal, universal approximator or a universal distribution approximator, I can increase the, I can increase the expressiveness or whatever by increasing the number of neural network parameters. So generative models are called generative for exactly that reason. They're used often to generate instances of data that haven't been seen before. And so, you know, you can, I would ask the audience if I was there, what kind of neural network you think this is, or what kind of machine learning strategy, but you'll probably guess. I'll show you on the next slide. But here's an unsupervised learning, you know, generative models strategy that's taken a very limited data set on the left-hand side. And it's very limited in the sense that there's actually only one element of the data set that's fed to it. It's a single picture of either Marilyn Monroe, Einstein, or Rasputin. And on the right-hand side, the generative model has been used to generate new images that have never been seen before, okay? And so all of those three pictures for each one of these famous people is basically extracted from the latent space of some neural network, which I'll show you. But the point is that they look fairly realistic, I mean, to the human eye. And so we tend to say, okay, well, the generative model has produced, you know, new instances of data that's drawn from the correct distribution. And what's nice about physics is we can actually, you know, quantify that. In sort of machine learning, we say, well, sure, you know, it looks like Einstein's head is rotated and his mouth is open. Looks pretty realistic to me. But, you know, in physics, when we actually have an idea of what the underlying distribution should be, you know, unlike what is the underlying distribution of all Rasputin photos, you know, it doesn't really make a lot of sense. We actually have a better chance in physics of sort of quantifying exactly how well our models are doing. So you might have guessed what that generative model was, and it lies on the implicit density branch of this structure that Leandro may remember we hashed out at KITP in 2019. So this is actually Michael Albergo's interpretation of Ian Goodfellow's classification of generative models. Michael Albergo, by the way, has used flow-based models now to sample. You know, I recommend everyone look up his papers with Fiala Shanahan and others. They've used flow-based models to do some amazing stuff in quantum field theories. Okay, so anyway, the structure, the sort of hierarchical structure of generative models that we're used to thinking about, starting on the left, you know, is maximum likelihood-based methods, which I just argued above are all related to, you know, this idea of Kullback-Leibler divergences and the idea that we have two distributions that we're trying to make the same, you know, through adjusting of parameters. So we have maximum likelihood. On the top branches in implicit density constructions that I'm not going to talk too much about, but of course, GANs are the most famous example. And all those pictures I was showing you before were generated by GANs. So GANs are implicit density because you know exactly what it sounds like. You don't have an explicit representation of a probability distribution, you have an implicit one. Okay, and GANs, as you may know, are trained through the competition between a generator and a discriminator. So what happens is you feed in a training set and you have a generator which produces, you know, fake images, whatever they are. And then you have a discriminator which, you know, basically tries to decide whether it's real or fake. And then you essentially backpropagate that real or fake label all the way back through the generator to try to improve it. But inside that generator, you know, there's no way of saying, okay, well, here's my amplitude, here's my phase, here's my mixing or anything like that. So, you know, GANs are implicit by very construction. So I'm going to stick to the explicit density branch, which is where most of the historical development of sort of quantum state reconstruction with neural networks is sort of focused. And you'll see exactly what I mean by explicit density through two examples. And I think the best example for anyone to learn about generative models is really a restricted Boltzmann machine. Restricted Boltzmann machines are sort of evolved from Hopfield networks. And John Hopfield was a condensed matter physicist, or is a condensed matter physicist. He's actually Bert Halpern and Steve Girvin's advisor. So, you know, back in the 80s, Hopfield was fooling around with Ising models as representations of distributions for machine learning. And so you see how a lot of this was driven by physicists, and it continues to be driven by physicists to this day. The restricted Boltzmann machine, which I've illustrated graphically here, is sort of an evolution of the Hopfield network, but has a lot of the same features. First off, it's an Ising model, okay? What that means is the green and the blue circles here are Ising variables plus 1 minus 1, whatever. They're usually zeros or ones in a Boltzmann machine. And they're connected not within layers, but between layers by the parameters that you're going to sort of adjust to get your, to get your quantum state, okay? And so those parameters are weights and biases. And you can see how the probability distribution is defined by, 1 over z, the partition function, e to the minus energy function. They call these energy-based models. And you'll see it's just an Ising model with your weights connecting visible and hidden units, okay? So most importantly, the number of visible units is the same as the number of your qubits. So when you have a projective measurement coming from a qubit, you feed it into the green units, and the hidden units, or the latent space, you can adjust the number of hidden nodes in order to get a more expressive machine. So for example, if you have a more highly entangled wave function, you might need more hidden units. If you have something that's has very small amounts of entanglement or very trivial correlations, you might get away with a very small number of hidden units. And you can also adjust the connectivity of the machine. So there's all sorts of tricks you can play with these things. I've been trying for years now to basically kill my research on restricted Boltzmann machines, because presumably there's all sorts of better models out there, and they just keep coming back, man. So, we still have projects on RBMs that are compelling to this day. So I really find them as they're really intuitive for physicists. They're a great way to learn about unsupervised learning, machine learning, and they actually have great utility for quantum reconstruction, which I'll show. However, I would also argue that, in 2021, there are more, I would say, expressive and easily trainable and powerful neural networks out there. A lot of them which were adopted from natural language processing models, and that's the tractable density branch. And what's the difference between the tractable density and the approximate density is really, in some sense, the idea that your distribution is normalized. So I'm not going to talk a lot about tractable density branch. Leandro's an expert, especially on the transformer side of things. So, make sure you bug him after my talk. But really, I've illustrated the most simple example of the tractable density branch, which is a recurrent neural network. And, the qubit state, which is X, is fed into some relatively complicated weight and bias transformation matrix inside the machine, along with a hidden vector H. And out pops, if you do everything right, a conditional probability with, the conditional probability of a qubit state I conditioned on all of the qubits to the left of it, say. And the equation I've shown there is the, what's it called? The chain rule of probabilities, which shows that if each one of these probabilities that comes out of an RNN is normalized, the product, which gives you a normalized joint distribution over all the variables, okay? So most of our current work between our group and Juan Carrasquilla's group in vector, I believe, is really on these sort of autoregressive models. So that's just something to keep in mind. I will continue to show you mostly results from the RBM. And I just wanted to say one more thing before I start showing you experimental results, just show you one more thing about how we sort of translate, or we transfer this technology from representing probability distributions to representing quantum states. And, the idea is something that's been developed over the last several years, again, largely driven by Giacomo Torlai. I think the first architecture on the left is really the generalization from a distribution to a pure state wave function, if you want to think about it like that. And all we've done here is we've replicated the Boltzmann machine. So we have visible units, I guess I'm calling them sigma, they're the green ones. And we have 2 sets of hidden units and connections, and corresponding weight connections. On the left is the usual amplitude, psi is square root of the probability distribution P. And on the right is the phase. And I haven't really explicitly shown exactly how this works, but you can just imagine that you have another set of parameters that is used to parameterize the phase of the wave function. And this kind of construction, this explicit density construction, although it's unnormalized, can be extended to mixed states through some purification techniques, which is, you can imagine, is the further replication of your hidden states into physical and ancillary units. So, okay, this is all basically fairly well established now. We know the structures, and we have all sorts of more sophisticated structures for generative models that can learn, all sorts of quantum states, basically whatever you need. And I just wanted to state that it's not the only strategy, RBMs again. So again, Leandro can tell you all about how other generative modeling strategies are possible on other generalized measurements or POVM type measurements, where you have more, I'd say, sophisticated ways of breaking up the sign or the phase, from the born kind of measurement distributions, if you will. And I think there's a lot of interesting work coming out in this front too. Okay, so maybe I'll pause if there's any questions before I get into an example here.
Thank you, Roger. This is very clear, very interesting to me.
Right.
I can see no hand raising in the audience for the moment.
Good. Let's get into the physics then.
Yeah, let's go. Yeah.
Okay. So I'm going to show you that this isn't more than just dreaming, although it's a lot of dreaming. But so I'm going to pick the simplest case. Okay. It's called a stochastic Hamiltonian. What is a stochastic Hamiltonian? As I mentioned, it's a Hamiltonian in a basis. You choose a computational basis, and a Hamiltonian is called stochastic if all of the off-diagonal matrix elements are negative in that basis. So it's a basis-dependent statement. And for me, as a quantum Monte Carlo person, that's equivalent to saying that this Hamiltonian has no sign problem. So it's the same class that you can use quantum Monte Carlo on. So if in that computational basis, a Hamiltonian is stochastic, then by the Perrin-Frobenius theorem, which is just a theorem of linear algebra, the extremal eigenvalues of the extremal eigenvalues, right? So, the eigenvector corresponding to the ground state, for example, the most important example, has coefficients that are all real and positive. Sorry, I kind of butchered that, but you get what I'm saying. So what it means is that the ground state wave function of a stochastic Hamiltonian is sign-free. And therefore, since you have no signs or phase structure, then there's a direct equivalence between the wave function and square root of the probability distribution. And that's also true if the probability distribution is parameterized by a generative model. So what that means is if you have a stochastic Hamiltonian, you can use any of the generative models that are out there in the machine learning world, RBMs, RNNs, transformers, GANs, anything to represent the state. And I'll just use the RBM because it's the only thing I know how to do. And now you're going to ask, how prevalent are stochastic Hamiltonians? And again, as someone who does Monte Carlo, they're everywhere. They're not everywhere you want them to be, but they crop up here and there. And one of the places where they've cropped up in the last, I guess, 20 years now, if I look at this, is in the Rydberg Blockade Hamiltonian. So this is the kind of fundamental Hamiltonian for a Rydberg atom quantum computer. And the Blockade Hamiltonian, which I've written here, has 3 terms. And so basically, it's operating on a qubit subspace of some sort of atom. And the 2 states of the atom are, because of the driving of a laser at the Rabi frequency omega, are the ground state and some highly excited state with, I don't know, n equals 100 or something like that, which we call a Rydberg state. Something just changed in my, do we have a question? Something just popped up, but it disappeared. Maybe not.
Yes, that's a question. Yes, from Abdullah. It's one of our guys remotely connected. Does the hidden state nodes, do the hidden states nodes in RBM entanglement you mentioned relate to the hidden variable theory of quantum mechanics? Oh, like a more fundamental.
Deep question.
So any connection between the hidden units in your RBM model and the hidden variable? I guess he's talking about Bell's theorem, kind of. Yeah.
So there's a paper by Steven Weinberg. No, did I get that name wrong? Okay, so there's been work on this. I'll get you the reference at the end. I'll post it in the chat. Okay, so people have thought about this, and there are some interpretations or some connections. Sorry, I just forgot. It's my colleague here at Waterloo, so don't tell him I forgot his name. But I'll get you the answer to that. But off the top of my head, it's something that, I'm not much of a quantum foundations person, let's just say, so I don't quite get to see the connection, but I can certainly point you in the right direction.
Great, thanks. Yeah.
Sorry for the non-answer. Any other questions?
No, I think that's clear. Yeah.
Okay, yeah. We'll come back to that.
Roger. Great. Yeah.
Okay, so the right, so this is my Hamiltonian for Rydberg atom system. So again, ground state, Rydberg highly excited state. That's the omega. The delta is a detuning, which breaks the symmetry between the ground state and the highly excited state. And what's interesting about Rydberg blockade Hamiltonians is the Vij term. So N is my Rydberg occupation. It's 1 if I'm in a highly excited state, or if it's 0 in the ground state, that's my qubit. And if two atoms are both in their Rydberg state, they have this repulsive interaction, or they have this energetic cost, which decays as 1/R6. So it's kind of a rapid decay. But what it does is sort of define, depending on the lattice spacing A, a blockade radius that two Rydberg atoms can't both be excited to their Rydberg state within. I said that weird. So we call these Rydberg atoms, but the state is the ground state of the Rydberg state. So you kind of have two Rydberg states within the blockade radius, which is I've kind of illustrated on the right. So this turns us into a strongly interacting, quantum mechanical Hamiltonian in the same sort of rough spirit as the transverse field Ising model. Honestly, there's a transformation you can imagine making between these two Hamiltonians. And of course, what's amazing is we have all sorts of experiments now which can produce very large arrays arranged by optical tweezers, very large array Rydberg atom arrays. And the one I work mostly with is Misha Lipkin's group in Harvard. Again, Misha has a spin out, a startup called QRC, which also produces Rydberg atom arrays. And if you're interested in this space, I recommend you look at what QRC is doing. So these are rubidium atoms. I won't go through the process of loading, rearranging, and readout. But what happens in these experiments is very large arrays, up to 256, I think, is the most recent published result. You can basically get a highly controlled, very pure, multi-qubit quantum computer out of these Rydberg atoms. I'm going to skip. There's a whole bunch of interesting phases in these phase diagrams for condensed matter people, but I'm going slow here, so I'll skip that. So I just want to show you the reconstruction of the data using a generative model. So here is an example of a one-dimensional Rydberg array. Because these use optical tweezers, you can make actually pretty much any lattice, 1, 2, 3-dimensional lattices and have them interact. Here's an example of one-dimensional lattices. I think the top bar there is everything in its ground state. And then you'll see various kind of Z2-like states. And on the lower right, you'll see a phase diagram. And these experiments kind of naturally can adiabatically tune the parameter delta from the disordered state, which is everything in its ground state, to these Z2, Z3, Z4 type insulating states. And so what we did is I like to say we hybridized the generative model with this experiment, but we just actually got data through email. But anyway, use your imagination. And we got 300 projective measurements, which is basically the limit of the shot budget for these types of experiments. And we assume positivity and purity of the wave function. And we use this data as a training set, just like I mentioned, for our generative models. And to make a long story short, we did a whole bunch of training. And then after the training, we used our generative model to produce estimators. And that's what I want to show you here. So the next couple slides are basically the main point of
so, Roger,
so this is results.
So your data set consisted only of 3,000 measurement shots
per detuning parameter.
I see.
And I forgot to mention, this is an 8 or 9 qubit system only. It's not exactly what I've shown above. So we trained this on 1, 2, 3, 4. That looks like a little bit too much, but I think it was 8 or 9. Okay. So you can imagine each one of these data points is 8 qubits, 3,000 measurements in the computational basis, which is informationally complete.
Okay.
So for you tomography experts, that's relevant. So you can ask what the sample complexity is and how that scales is the number of qubits. And that's something we actually thought about a bit too. So here's a very simple kind of demonstration of how the generative model works. Okay, so I have 3 curves on this plot. One is ED, which is exact diagonalization. That's why we did 8 atoms, is because we can exactly do all of the adiabatic time evolution of the Hamiltonian and you know, Hamiltonian driven simulation is what that is. The exp is the experiment. So that's the data driven. That's actually just the raw data, because what I'm illustrating here is, so 1 point, you know, so I have sigma z, but it's just a transformation. So on the left-hand side of this plot, everything in its ground state. And on the right-hand side, you see the data there, everything, you know, the system's in its Z2 state. So the experiment in this diagonal basis is very clear. And the triangles are the reconstruction of the generative model. And again, we assume stochasticity, if that's a word, and positivity, so purity of the wave function. And all we do is reconstruct the state by Kullback-Leibler divergence, stochastic gradient descent, get P of lambda. And then on the lower left, you see how we calculate diagonal observables. So everything works perfect. And you're left wondering why bother.
But let me ask you something, Roger. May I ask you something? So sorry about the experiment. So this delta. So what's the role of this delta? So is this like adiabatic? This is like adiabatic passage, right? So you go through towards the ground state, right? Or what is this delta? The meaning?
So delta is just a parameter in the Hamiltonian. So we're assuming that every one of these data points, the system's in equilibrium at that delta.
Right.
Okay. It's prepared adiabatically.
They prepare adiabatically the ground state or some equilibrium state.
Yeah.
With that Hamiltonian, depending on that.
Right.
And then the second question is, okay, so since the Hamiltonian is stochastic, you know that there will be no sign problem, and then you can apply your nice model and mapping between amplitudes and probabilities nicely because you don't have the sign issue. But then, sorry, the ground state is not like, so you said that the measurements were in the computational basis, but the eigenvectors of the Hamiltonian are in the computational basis states, or this is the part that I'm a bit confused.
Right. So N
because
here,
the Hamiltonian doesn't suffer the sign problem in one basis, but then you need to measure in the same basis, right?
And that's what's done. Okay. Yeah. Yeah.
And is that the computational basis?
Yeah. Yeah. So like, I'm calling the basis, the computational basis, the occupation basis N here. So N is 0 or 1. It's the occupation of a Rydberg state. And so if that's diagonal, delta's diagonal, and the off diagonal piece, and maybe this is where your questions comes from, is omega, but omega has to be negative here in order for this to be stochastic.
Right.
So I actually, if anyone followed my argument with the stochastic, with this looks like it's the wrong sign. But, and that's, so my mistake. And the reason I did this is because the unitary transformation to make this stochastic is trivial. Yeah. It's a unitary that occurs, you know, it's a depth 1 quantum circuit with a unitary on every site or something like that. So it's just, I'm so used to assuming that this can be done that I forgot about it here. But so that Hamiltonian with minus omega or omega negative that's a simple unitary that makes this thing stochastic. So if you have single site operators on the off diagonal part of the Hamiltonian, those can always be made stochastic with a trivial unitary. It's only in the case where you have like 2 body interactions in the off diagonal part of the Hamiltonian where this gets tricky. So transverse field Ising models basically are always easily made stochastic.
Yeah, thank you.
Right, and so the data has to come out in N occupation, and that's what this is. All of this data is the Rydberg occupation. So it fluoresces in the ground state and doesn't in the Rydberg excited state. There's just a dark spot. And so that's the qubit measurement, you know, in the N basis. So that's why we can do this type of reconstruction. And so that's actually like, I'm trying to illustrate the data in these bars here. That's base, you know, we have 3,000 of these per triangle, and that's how we reconstruct. And so why do we do it? This is kind of the illustration of why. This is where the power of a generative model comes in. Here's the sigma x expectation value, okay? And so that's, you know, that operator that I defined in going between ground state and excited state. And
Roger, let me interrupt you again. I think there is a question from the audience.
Perfect.
Is on? Can you hear me?
Hi, Andreas. Yes, we can hear you.
Oh, also now, you hear me?
Oh, no. Now we cannot hear you.
You're pretty quiet.
Can you speak closer to the microphone, Andreas? Your mouth close.
Before you had this curve with the 3 lines, and it was astonishing that everything was perfect. I mean, even the experiment. I
agree.
This normal?
I think it's, you know, I don't want to speak for the experimentalists, but I think it has to do with the small size of this system. So I have, you know, if I look at these are more recent measurements on very large systems up to 219 or 256 atoms. I would say that there's not perfect correspondence between, you know, number one, you don't necessarily have a sort of Hamiltonian driven data for everything on these large system sizes. But I think one of the points of doing this is that as the system sizes increase in the experiment, you know, we want to see the level of our ability to control these things. And so again, you know, I think systematically you imagine starting with a small system size where everything works perfect, which I'll get to. There's a caveat, you know, and then we increase the system size and hope that things work better. But also to answer your question, things aren't perfect. And that's this slide here.
Okay, thank you.
So
Thank you, Andreas.
Yeah, Andreas, we can come back to this question after, but let me show you this. Okay, so actually I'm going to use my mouse here. I don't know if you can see my mouse. So here is why we do this. And again, this looks perfect, but now let's look in the off diagonal basis. And so here's a measurement of sigma x, which is off diagonal. And I have ED, which is the exact diagonalization of the, you know, full preparation of the state. And I don't have any experimental data in the sigma x basis. I only have Rydberg occupations. That's all we can do. But I can reconstruct the state in the restricted Boltzmann machine from the diagonal basis because it's, you know, informationally complete in that basis. And I can do this trick that we use in variational Monte Carlo that Juan taught me, you know, which is basically measuring off diagonal matrix elements, you know, in the usual way, but then repackaging things into a local estimator. And as long as the object in this rectangular box is sparse enough, then I can, you know, then I can reconstruct off diagonal observables from this trick. And so we've done that, and that's the restricted Boltzmann machine triangles here. And so unlike the diagonal case where everything worked perfect, you see that there's a fairly serious discrepancy between what the data-driven reconstruction gives us in the machine learning model, that's the triangles, and the exact diagonalization of, you know, the Hamiltonian driven. So here I should call this Hamiltonian driven as the line and data driven as the triangles. And so again, to answer your question further, not everything's perfect. And, you know, basically the experimentalists used this evidence to iterate a few times and they improved a lot of their control. So actually this never made it into the final paper. But I think this is a really great example of how machine learning, you know, helped inform the experiments to, you know, in this case, you can almost see here that there's got to be some sort of detuning problem. Like you're not getting into the delta regime you think you're getting into, right? Because things kind of saturate. And so again, maybe this is an answer to your question. You know, this is how I imagine that this is useful. These reconstruction techniques is to give feedback to the experimentalists on issues like this. So I think we're almost out of time.
Roger, this is very, very interesting. Let me ask you something, because this is really interesting. So hold on. So you said, okay, the ground state is a product state, right? In this, it's always a product state, right? In the computational basis, or did I miss that point?
No, it can be. So here's the entanglement. We can have entanglement entropies.
All right. Yeah, I see. So it's just the only guarantee that you have is just that the guarantees that you have is that the amplitudes in the computational basis are all positive. That's your promise, right?
Yeah.
Because
this is the only, yeah.
All right, I see. And so this means that there are no complex phases, right?
Correct.
And so where is the discrepancy coming from? Like what caused this?
This?
This
is, I would call it experimental details because I'm a theorist. But I think this is the crux of the matter. This is what's so interesting. So it can come from experimental details, which largely were fixed after this, or it could come from, the fact that we may not be learning correctly, right? Like my generative model, which gives me the triangles, could not be learning the correct ground state. Because that's certainly a possibility.
Right, because if you have the promise that there are no complex phases and all the amplitudes are positive, then your measurements in the computational basis are informationally complete, and this you mentioned, right? So there's all the information is there, right? Okay.
Right.
Okay. Cool.
So you can also have a sample complexity issue. You could also say, well, I don't have enough information coming from the device. So
sure, and especially because this Ising models encode very complex, computationally complex problems, right? So yeah.
Exactly.
Let me pass the mic to a question from the audience. Okay.
Sure.
So.
Yes, I mean, Roger, thank you very much. Could you clarify this a bit more? I mean, like, there are samples coming from the device, so you could also like directly feed it into the estimator and then get like a much cruder estimate than like your resampled thing with like where you actually had to learn the RBM and you're biasing it using your model in a sense, like the estimator. So how does the sample complexity compare, and how like, I mean, how bad am I if I don't train a model in between?
Right, good question. So this is these two different philosophies. No, on the left is you're not training a model, and on the right you're training a model. And okay, let me. So here is. So let me just remember how this looks. Okay, so this is the fidelity of the reconstruction in both cases. So you'll see what happens is FD is frequency distribution and RBM is the solid line. So you'll see around the size that we're looking at, around 8, 9, 10, 11, 12, depending on what fidelities you like, you'll see a rapid drop off of the fidelity for this number of, and I think this might still be, here's a number here. So this is still 1 × 10⁻³ on the top. Sample complexity. So there's a trade-off between sample complexity and fidelity that drops off somewhere around order 10, but it depends a lot on these parameters, right? So this is a full kind of study you can imagine doing yourself.
Okay, but like this fidelity, is this now like compared to the exact ground state?
Right, or the yeah. So we still have we can only do fidelities up to a certain size because of that, right?
Okay, so best case, you're kind of like the RBM is fooling in the direct direction. Like, or is this all synthetic data?
This was synthetic data, and we did a lot of studies on synthetic data because we have Monte Carlo simulations and DMRG simulations. And so actually we did a lot of work, and I won't explain this, but we did a lot of work on scaling in terms of number of hidden units and sample complexity up to hundreds of Rydberg atoms. So you can see we have scaling plots. This is actually transverse field Ising models. But so one thing we do in my group is we characterize all of these types of, the performance of these machines or these modeling strategies based on different sample complexities and different expressiveness of the machines and so on. So your question has an answer, and it's a fairly complicated, I'd say balance between, again, the amount of samples you have, the number of parameters in the machine and so on. So my contention is this is like, we're kind of at this frontier now where modeling is starting to help. But for smaller sizes, definitely, you should do the frequency distribution if you can get enough data.
Okay, thank you.
Cool.
Thank you, Ingo. Thanks for the question. So, okay.
How much time should I spend here, Leandro?
So we started at 5 minutes after 10. We have some 8 more minutes, 7.
Let me wrap up in like 5 minutes here.
Yeah, exactly, because there may be another question, but this is all very interesting, Roger. Very nice. Thanks. Congratulations for the great results. Yeah. Let
me just show one more result, which I love, is that you can reconstruct this second Renyi entropy. And I don't know why I love it so much, but so this is a scalable technique that we stole from Monte Carlo methods, and we applied to the reconstructed models. So again, I'm hoping I'm giving you an idea of what's possible. And here again, okay, I have an 8 Rydberg atom system, and I have 3 bipartitions into region A and B, because the bipartite entanglement entropy for 2, 3, and 4 Rydberg atoms. So I abused N there. N is the size of my bipartition. And again, this is data reconstructed in a restricted Boltzmann machine only from 3,000 measurements that have been produced by the experiment, okay, in the occupation basis. And then what we do is we use a swap estimator trick, which I can explain another time, which is basically replicating. In finite temperature, you replicate the system on like a multi-sheeted Riemann surface, but at 0 temperature, it's kind of simpler. You can write as this tensor network notation. So you can basically do this in the restricted Boltzmann machine or in any generative model. And so instead of, trying to find clever ways of measuring your entanglement entropy, directly in the device or so on, you can essentially just, if you can reconstruct the ground state in the generative model, you can do entanglement entropy measures directly in that model. And these are, I don't exactly know the scalability of these swap-like measurements, but in Monte Carlo, we easily measure entanglement entropies for systems of thousands or tens of thousands of atoms. So, okay, so, of course, this is all sign-free. If we want to go to signed wave functions, with phases, or we want to go to mixed states, of course, there is some mixing that we're kind of ignoring, but if we want to be more careful there, basically we use these other architectures, and that's where you get into kind of tomographic issues like informational completeness of the basis. But everything is, in terms of the model, is easy to generalize. The Kullback-Leibler divergence, or the maximum, or maximum likelihood estimation, can easily be adapted to having, different numbers of bases. Here's the time evolution. I forget how many atoms here. Giacomo Torlai did this. We never published it. So here's a Rydberg, here's Rydberg atoms under time evolution, where you quenched, to a Z2 state at t equals 0, and then you're letting the system time evolve. And so this is the comparison between Hamiltonian driven, which is the black line, and then we produce synthetic data and we reconstruct both the diagonal measurement and the second Renyi entropy. Because I don't know, I figure once you have the entanglement entropy, it's almost like the fidelity in some sense. It's pretty sensitive that, all sorts of different things that can go wrong. And then a note here is that, and again, I'm not a tomography expert, but this is a local Hamiltonian that's fairly simple in terms of its structure. And these results were obtained with a linear number of bases. Okay, so different numbers of bases. You can go anywhere from 1 in the stochastic case to whatever it is, 3 to the n or 4 to the n in the fully general case. And I'm sure there's lots of room to explore in between there. So just a real quick recap. So where's the frontier here? We have all sorts of great neural network ansatz. They're not necessarily constrained by area law like tensor networks are. They do have other types of inductive bias. And, I would argue that autoregressive models are the future. The trends, the interplay between, I would say, sample complexity and inductive bias isn't really clear to me. I think there's a lot of stuff to explore there still. If you have highly constrained models, maybe you need less amounts of data, or smaller sample complexity, a wide open field. And there's, relationships to things like shadow tomography and so on, which, is now, sort of the bon ton of non-tomographic reconstruction. But I would argue that Juan and Leandro also kind of invented in this Nature Machine Intelligence paper before Preskel. You heard it here first. And I would also argue that like optimization is really where we have to think about what we're doing. Lots of times there's an urge to take, all this complexity and just say, okay, well, the optimization, we'll handle this somehow. But what we learned from variational Monte Carlo studies on spin liquids is you can't just be sure that the optimization procedure is always going to work. There's a lot of heuristics that go into this. And I also think, there's a lot of kind of foundational work that can still be done on the optimization part of this learning. So even though you have the data coming from the experiment, can you do the optimization to reconstruct it? I think that's a big open question. So that's it. I'll leave this up. Standard generative models can be easily adapted to reconstruct states with all sorts of caveats. I didn't talk about variational methods, like Hamiltonian-driven methods. But of course, there's a huge amount of work on Hamiltonian-driven methods that are inspired by generative models, right? And so the idea is, you can just throw out the, throw out the data and bring the Hamiltonian back and use these same structures. And in these structures, again, are always, we're always getting new input from, I'd say, the machine learning community. And I would argue that, these new types of autoregressive models like transformers, or as I've illustrated here, two-dimensional RNNs are extremely powerful, and almost, there's been almost no work on these things. So a ton of low-hanging fruit. I would really recommend, looking at Mohammed Hibet Allah's work and basically thinking about how two-dimensional RNNs could be used both in the variational and the data-driven setting. And then finally, what's the future of all this? Well, this study that I put at the bottom is super interesting. You can imagine that, you take the data from the experiment, you train the generative model, and, once you exhaust your data, you can say, well, I have a pretty good assumption on the Hamiltonian that I think is in that experiment. Let me do a certain number of variational steps after the training. Or maybe you do the variational steps first, try to do the early phase training variationally, and then just kind of like do a bit more training with a limited data set. Or you do some sort of transfer learning where you maybe adjust the parameters in your model and you try to, use data from that model just through the final stage of training. So I think in the future, we're going to see a lot more of this hybridized approach where, we have an experimental device, we have limited shot budgets, there's some cost to the data, we have a pretty good idea what the Hamiltonian is, and we combine both of these approaches into one sort of generative model that's been trained both by Hamiltonian and data-driven learning. And then the lines between, experiment and modeling will be blurred a bit, but I think really we're going to see a lot of progress on a lot of these interesting problems with that technique. So, okay, thank you very much, everybody.
Thank you. Thank you so much, Roger, for the great talk. This is really, really interesting, the perspectives. This is really nice. So Roger's already been talking. Oh, great. Thank you. Thanks for that. It worked. Thank you, Aaron. Thank you, Ingo. It worked.
Thank you, audience.
This is really nice. I don't know if is there any other question, like a last minute question? Roger's already been talking for a long time and he's already answered some questions, but if there's some question by some of the, typically I prefer questions by the more junior researchers. If there's, raise hands, great. So the pressure worked. Who's gonna ask something? Oh, Andreas, okay, great.
I just want to know what RNN is. Is R neural network?
Is the question, what is an RNN?
Yes.
Yeah. Sorry, yeah, that's it's too easy to jump into jargon. So it's a recurrent neural network, and it's recurrent because there's actually only one sort of what they call recurrent cell, and you feed in a qubit state and a hidden vector, which you don't have to worry about. It outputs the probability of that qubit, the next qubit down the chain being either up or down, conditioned on all the previous qubits. And then that probability is used to sample another qubit, and the hidden state and that qubit state is fed back into the same machine. So it's a recurrent or a recursive function. And these are often used for natural language problems. So, because you imagine each one of these X's is actually a word chosen from a dictionary. You know, forget a qubit with only 2 states. Typically your input is your entire, you know, the Hilbert space is your entire dictionary. So these things are very, very powerful. This is how you do translation, you know, English, French translation, or text completion. So, you know, oftentimes you'll feed in the starting words of a sentence, and this thing will complete your sentence. And because I get a couple extra seconds here, here's another way to use a recurrent neural network is for time evolution. So this is a different simulation. This is you know, a single ion Rabi flop, you know, from a trapped ion experiment here at Waterloo. Here's training data. Each one of these blue points is like a word chosen from a dictionary. Here's my sentence being constructed. Then we chop off the training data and we ask the RNN to complete the sentence. And that's the, you know, Rabi flop here. So we can do time prediction, or, you know, time evolution with these methods, which I think is really useful for
it totally learned the dynamics. It totally learned it. Yeah. And I guess that people from finance are interested in these things for price predictions and things like those too, right? For anything.
Yeah, exactly. There's a million applications for this, I think.
Yeah.
Thanks for the question. Thanks for the softball.
Thanks for the question, Andreas. Is there any other question there? I cannot see. Wait. It's difficult to see. No, I think no. All right. I think this has been very clear. This has been a very clear talk and also very comprehensive and self-contained. Thank you for that, Roger. We very much appreciate. Oh, wait. There is, hold on. Do we have this somebody here? No, that was not. Hold on. You've mentioned, oh yeah, hold on. Yeah, there is a question here, sorry. You've mentioned that due to the lack of data, we usually use the cos function instead of the Hamiltonian. How exactly does the cos function compensate the Hamiltonian? Well, okay, this is... I
would say it's not necessarily due to lack of data, but, you know, I imagine in the near future, we're going to have data from devices that we can't simulate with the Hamiltonian. I think that's where it gets interesting, right? And Marcus Greiner and other people have, you know, data for, you know, let's say atomic, you know, emulations of things like a Hubbard model. So here I am, I have the Hamiltonian, but I can't do anything with it. It's got the sign problem, it's 2-dimensional, DMRG doesn't work. So that's where it's interesting. This is like coming up in the next 2 or 3 years, right? People will construct Hamiltonians in a simulator, whatever the device is. And it's going to be something that I can't do the Hamiltonian driven simulation on.